We all know behavior trees, but state trees are a new and exciting way to get our AI behavior and actually a lot of other fun stuff working in Unreal. So let's enable it. We'll go into the plugins. If you don't have the plugins tab yet, you can go up into edit and enable it right there. And we will look for the state tree plugins, where we will enable both the gameplay state tree and normal state tree plugins, restart the projects to load them in, and then we can get started. So state trees by default will actually work very similarly to behavior trees in a lot of ways, but give you a lot more flexibility because they also support pretty much the exact same way of transitioning between different states or tasks as a state machine would. That's why they're called state trees, because they are a combination of state machines and behavior trees. So let's make one and we can start looking at all the bells and whistles that we have with them. So you can just make them by going into the artificial intelligence and state tree. Now that we have this thing enabled, then we get the schema that we can pick. We can either pick a normal state tree component or a state tree AI component. If you're working with C++, I do believe you can make custom schemas that will also show up here. I haven't looked into that because by and large, that's not necessary to do. If you have certain state trees that really need to only be used on certain types of actors that have certain unique data that the state tree is going to need to use, it might be nice to have that all automatically provided in with a custom schema, but it's by no means necessary. So we're not going to bother with any of that stuff in here. So we'll limit it to the normal state tree component and the state tree AI component. As a general rule, the only difference is the schema that it uses, so the default data that it provides, and also on what kind of object it runs. The state tree component schema will run on state tree components that are on the actors themselves. Wonderful thing about that is that it doesn't need an AI controller to function. So unlike something like a behavior tree that needs to be run on an AI controller, so it needs to be working with a pawn. It can't work with a normal, just regular actor. State trees can run on regular actors without a need for any AI controller related stuff. State tree AI components run on the AI controllers, which can be nice if you have a specific controller that needs to give behavior to a bunch of different possessed actors that just share the same type of controller. So if you have just basic animals in your game that just need to wander around and run away when the player gets near, something like that, you can just make an AI controller that has the state tree for that on it, and then anything that has that AI controller will behave like that. In this series, we're going to mostly use the normal state tree component. I'll show you the differences between the two in a moment, and we're going to still do some AI controller based stuff because the examples that I'm going to show are going to be moving around, which requires an AI controller. But I like personally putting these things on the actors themselves. So let's open up the state tree and let's look at what the interface has to offer, because there's quite a few things here to talk about. And immediately let's start off with the schema, because that is, again, effectively the only difference between the state tree component and the state tree AI component. After you make one of these, as you can see, you can just switch back and forth between the two different schemas anyway, or whatever other schemas you might have custom made in C++. So if I change to the AI component one, this will make this expect to be run on an AI controller. And we'll see that the context variables here, which has only actor in it, will change to having the actor and AI controller, which also changes the fields that we have down here from only one thing for the actor class to two things for the actor class and the AI controller class. So what are these? These are the classes for the context variables. And what are the context variables? The context variables are variables that we can automatically supply in to our tasks for whenever we need something to reference the actor that we're working with. That will become a little bit more clear in the next video when we actually dive into making custom tasks though. For now, all that we need to really worry about is the fact that we can either keep this very generic so that it can run on a variety of different things, or we can do something like, I'm just going to make a character here and we'll call that state tree character. And I will populate all these things in a moment. But we can also just change the actor class here to specifically state tree character, which will now allow us to access specific variables created on the state tree character class, either within the individual tasks or within this interface. Again, this will become more relevant in the next video. If it doesn't fully make sense right now, don't worry. As you will see examples, hopefully it'll start making a little more sense. For now, though, we are going to stick with the normal state tree components, which will also reset this actor class thing. But again, we'll worry about like setting all that up properly once we actually get into the examples of things. Next up down the list, we have the parameters, which is exactly what it sounds like. It's just effectively variables for your state tree, except that these are variables that aren't necessarily meant to change. Unlike something like a blackboard with blackboard keys that are effectively also variables for your behavior tree, these are meant to mostly just be set once and then not be touched anymore. There are ways, either in C++ or in recent updates also through Blueprint, to set these as well. It is possible. In my experience, that causes a lot of crashing in packaged builds because the state trees have some kind of bug in them where it's not properly referencing these values. If you're watching this in the future, I'm sure that that's been fixed, but for now, we're going to avoid setting these parameters. We're only going to be reading from them. You can set them just in this interface, no problem, right? We can just make this and call this like walk distance or something like that. Very badly spelled. And you can set them to whatever you want here. Like you can set them up in advance. You just shouldn't set them on runtime. There's a lot of workarounds for that we'll discuss. And in the future, maybe it'll work. But if you're going to be messing with these things, before you get in too deep, package your game, make a standalone build, and test whether or not it actually works in that as well. Because in my experience, there is a bit of a discrepancy between how they function in editor and how they function in a standalone build when you're trying to set these during runtime. We're going to ignore evaluators and global tasks for the time being, because those can be videos all to themselves. So let's move on to the theme. These are just pretty little colors that you can give your states in your state tree. So we can say, we want to have a red color for when they are angry. And then we want to have maybe a, I don't know, yellow color. I like yellow. For when they are scared, and so on and so forth. These functionally don't do anything. These are just there to make your state tree more readable for you as a developer. So if we go into one of these states, which finally, we're talking about state trees, right? Let's go into one of the states and look at the details that we have for those. We can set the color, right? From angry to scared to default to whatever we want. Not all that relevant. You can see that each state in itself also has some parameters. Ideally, once these are actually settable and they don't crash the game when you set them, this might be a cool way to effectively have like local variables within a state that you can set and reference back to. For the time being, again, setting these on runtime is a little bit tricky and not very stable. So don't worry so much about these parameters for the time being. We have an enter condition and some transitions, which we'll make a separate video about. And then we have got tasks, which again, I'll make a separate video about. This is just an overview for you to understand how the structure of all the states works. The next video will be about tasks, and after we'll talk about like conditions and that kind of stuff. For now, I want to talk about the different type of selection behavior first, and then we'll talk about the different types of states as well. So the selection behavior is mostly to do with being selected and what it selects. So if we go through the route, we can make a couple of child states. You can right click and add states this way, or you can add states just through the add state button. But this is a little bit more precise, where you can add either sibling states. So that's a state on the same hierarchical level as the state that you're currently clicking on. So in this case, these are part of the same parent state. In this case, that's no parent state. Or you can add a child state, which adds a state that is linked to this as a child. It is important to realize that once this state is selected, this state is not considered unselected necessarily. When a child state is selected, it also counts as the parent state being selected. And the reason that's important is because you can explicitly go immediately into a child state, which will also activate every parent of that state in turn. That'll probably make sense a little bit later if it doesn't right now. So let's add a couple more child states to this to show off what try select children in order does. Because this is the root, and the state tree is effectively just going to start off with the root state. And the root state is just the topmost state in this interface. So if I make a sibling state to this and I put that here, it's going to try to enter this one first. It's just whatever is in this position is the first thing that's getting entered. So then when this thing is selected, it will try to select its children in order. So it's going to try to select this one first, and based on its enter conditions, it's going to check, hey, can I enter this, yes or no? If no, it's going to move on to the next, and it does the same thing until it finds something that it can enter, which is exactly the way that a behavior tree would function. So by default, if you don't set up any transitions whatsoever, it's just going to behave like a behavior tree. And as you can see here, at the end of every state, we have this thing that says back to root. So after a state is done, it's going to go back to root and do everything all over again. Once again, exactly the way that a behavior tree functions. A state tree is just a state machine that behaves like a behavior tree. It's the best of both worlds. But selection behavior doesn't just stop with trying to select the children in order. We also have none, which makes this state unselectable. I frankly have no idea why you would do this. Straight up. No idea why this exists, but it does. So doing this makes it unselectable. If we just go into here and we make a transition real quick, you can see that it gives you an error because you can't enter the root state. I suppose if you want to explicitly enter one of these states, and then also want this to be considered active because it has some tasks on it, that you don't want to directly be able to only do this, that's where none comes in. I don't see too much use for that, but it is technically a possibility, I guess. The much more useful version of that is try enter. What this will do is it will just enter this state, but not try to activate any of the child states. So we can explicitly just enter this and do whatever tasks are on this state without bothering with any of the child states. But if we go into any of the child states, it will do both whatever is on this and the child states. As a fair warning, that also means that if this completes before whatever child state completes, that this is going to be marked as completed and it's going to do its transition, which either is going to go back to like root or restart the tree or whatever, and it doesn't necessarily wait for the child to be finished. The other way around as well. It's just whichever one finishes first is going to do its transition. Then we have the try selecting children in order, which we talked about, and we have try follow transitions. This is effectively just a, hey, I want to set up my own logic for what you should do, just like make my own transitions with conditions and all that kind of stuff. The difference is for try follow transitions is that if it finds any transition that it can do, it will do that instead of its own task. So it never actually starts with its own task if it can transition through. Whereas when you do try enter, at least the task will get started and then it will start doing transitions. Which brings us to the types of states that we can do. The most basic one, which most of the states are going to be, is a state. This is a state that can contain child states, like all of these. And this can nest as deeply as you want, right? So you can make a child state and a child state and a child state, and they can all like, whenever we do this, it'll also have this and this and this all active. So that's child states, but it can also contain tasks, which is like actual like code to run, which is what the behavior is going to like be based on. Then we have a group. A group is effectively just a state without tasks. You can see as I go back and forth between a state and group, it just makes the task little thing here disappear. This is purely for organizational purposes. So let's set this back to try and select an order. We can select this as a state to go to. It won't have any code of its own to run. It'll just be a redirector to like whatever child state that we're going to go in. Quite useful. Next up though, we have linked. And for linked, we need to talk about SubTree first. So you can mark a specific state here. Let's say this one, as a subtree, and let's call this subtree. Usually it makes more sense to make this like an actually like separate thing altogether from the tree that we're working with, but it doesn't have to be. And when we set this to being linked, we can link it to anything that is marked as being a subtree. And what it will effectively do is whenever we get to this state, so it would make more sense to do that on like a child state, like all the way down here, like linked. When we get to this, it's just going to run whatever subtree we link it to as this state. So a state tree has this concept of being able to be finished as one of its transitions. So we can say here, if we like on state complete, we can mark this as, instead of transitioning to something, as the whole tree having succeeded or failed. And when it does that, it finishes the subtree and it marks this state as completed. So you can have this entire subtrees accessible and run them as a singular state. I personally don't love doing this because of the next thing that we can do instead of doing a subtree is we can use a linked asset. This effectively works the same way, but instead of making a subtree within this state tree view, you can just link an entirely like separate asset that it will run until it is marked as being completed, and that will then mark the completion of that state. The upside of that is that you can make many more modular small pieces. Like if you have a character that needs to have a patrol routine, right? It starts at a location, then it finds something to walk to, then it walks to there, wait for a couple of seconds, find a new location, walk to there, wait for a couple of seconds. Something fairly simple. Of course, it can be more complex than that, but a lot of your characters are probably going to need to use that. So you can make a state tree specifically for that and then just use this as like a linked asset. So anytime a character needs to patrol, you can just link it to that other state tree, and that is effectively like a sub state tree. That makes the code a lot more modular, a lot more reusable than using these linked subtrees, which is also a possibility and sometimes might be nicer to do, but I personally think that using linked assets is a little bit smoother to work with. So those are all the types of states that we can have. Now, none of this does anything yet because we need to actually like start programming some tasks for this. So let's just remove all of these and we're going to change this back to being a state. The root usually can actually be a group instead if you want to, but we're going to just change it back to being a state, everything back to default, and we'll make a character that has this state tree on it real quick. So I already made this state tree character class, and here we simply just add a state tree component. Again, if you're making the state tree AI schema, you're going to need to add the state tree AI component, and you need to add that on the AI controller, not on the character itself. We're going to stick with state tree normal here. Apparently, I already added one of those. So in there, you have this state tree AI thing, and you can see we can pick our schemas here. We only have one schema, and I already picked it. And here, we can even change the walk distance parameter. Remember the parameter that we made, the walk distance that I said you can't write to? You can very much just say, hey, I want to set a custom value here. Like I want to make this 1500 for this type of character. And then whenever we use this walk distance in any of our tasks, it's going to use whatever value we gave in there because it's just a variable. We can say whether or not it should start the logic automatically and all that kind of good stuff. So let's add in a child state real quick. And we're going to just add in a task, debug text task. And the text will just be hello, just so that we can see that it's actually running. We'll talk more about tasks in the future. I already put it in the world as well. So now when we run this, we should be able to see right there, it says hello. This actually seems a little bit broken because it's supposed to use the actor as the location, and this should be the offset, but apparently it's doing this as world location. But we can see that the debug task that we apply it to, the hello, is getting added to the world there as a debug thing. So our state tree is running. Congratulations, and you have technically added your first task. It doesn't really do anything yet, but I think this is quite enough for the first part here. So we've run through all this so that you have a basic understanding of where everything is and what kind of things they do. If you aren't really following along in a lot of detail yet, don't worry. As we start going through and actually making stuff, all of this information will start to click into place and you'll start to understand what is actually going on. But now that you have all of this basic knowledge of like what all of these little different things are, we actually can start to use them. Now that we understand the basics of what a state tree is and how all of these things work, we're going to go through and actually talk about how to make them useful. Because in the last video, all that we managed to end up with is saying hello at the 000 position of the world, and well, while that is fun, it's not actually that useful. So let's talk about making some tasks. Now, if we open up our state tree that we made, we already added a task, the debug text task, which seems to be a little iffy with the way it works, because this offset is supposed to be an offset from the character that it's running on, but that doesn't seem to be working, because it's just the world position for some reason. But that doesn't really matter for what we're doing right now, because we can just remove this, because we're going to be making our own tasks. Now, I should point out that if you're using a state tree AI schema, you have one more default task available to you, because we have AI actions move to. This requires an AI controller to work, of course, because it just uses the move to function from the AI controller, wrapped up in a nice little task. We can replicate that effectively so that we can use it on a non-AI version of the schema instead. And the reason that we would do that is because we want to put the state trees on the character classes themselves instead of on the AI controllers, because we want to be able to set things on a more like individual basis, or it just makes a lot more sense personally to me to be able to do that. So let's get started with a handful of things. We need a move to task, and then we need something that will figure out what location we'll move to. And we're going to make those two separate tasks. You might want to make that one singular task in practice, but I want to show you a couple of things of sharing data between different tasks as well. So we're going to make that into two separate tasks for mostly educational purposes. So let's get started by making our AI move to task. You can just do that by going to your blueprint, typing in task under all classes, and finding the state tree task blueprint base. I personally mark these with STT for state tree task. Move to non-AI. In here, we have a couple of things that we can override. The enter state, so this runs whenever the state that this task is on is entered. The exit state, this runs whenever we exit the state that we were on. State completed, which does a similar thing. It runs whenever the state we're on is completed. This has a little bit more intelligent logic to it, where it does it in the proper hierarchy. Exit state is, I believe, not so consistent in the order that it does things, because state completed is called right after the state has been completed, as it says here as well. But for most use cases, these two are effectively interchangeable. And then we have tick, which will just run every frame as long as the state that this task is on is active. So for this, what we're going to do is we're going to enter state. So whenever we enter the state, we want to move to a location. So for that, we'll first need a location to move to. So move to location, which will be a vector, and we'll expose that. Now, we also want to get the actor that we're running this on, because we don't have like default access to that. So we'll make a variable called actor, which will be of type actor, and we'll expose that as well. We're going to make this more intelligent and a little bit automated in a moment, but I want to show you the basic setup first. So we'll get the actor, and we'll actually get the AI controller off of it to check whether or not it has an AI controller. Because even though we're running this on a non-AI controller tree, we're going to be using an AI controller function, so it needs to have an AI controller to work. So we're going to get AI controller, and we're going to check if that is valid. Because if this AI controller is not valid, we want to just immediately finish the task and mark it as unsuccessful. We'll talk a little bit more about finish task in a moment, because this is poorly named. This should be finish state. If you have multiple tasks on something, it's not going to do those tasks one after the other necessarily. It's going to run them pretty much all at the same time. And whenever any one of them gets to a finished task, it finishes the entire state. Anyway, if the AI controller is found, we can do move to location or actor. The reason that we're doing this one is because this one is latent. So it has these pins for on request failed or on move finished, which is quite important. If we just use the normal move to location, this will just start the move, but it won't give us any feedback as to when the move is finished. And that's going to be important for what we want to do here. So we can give in either a goal actor or a goal destination, which is going to go for a goal destination at the moment. You can make this also take in an actor, I believe the actor input takes priority over the location. So if you put in both, it's going to go for the actor. But that's not really like too relevant right now. We just want to have the move to location. And then when either the request fails or when the move is finished, we'll again finish task. On request failed, we'll see this as being not successful. And when the move is finished, we'll say that this is successful. This can influence the different types of transitions that we go into. Based on, hey, did we reach our goal or not? We might want to go into a different state entirely. But this effectively is our first task. So we more or less just recreated the AI move to task on something that now can exist on the actor itself instead of having to be run specifically on the AI controller, which is just kind of nice if you ask me. So going back into the state tree, we can see we have this thing over here. Let's call this patrol, and we add the task there. The task that we'll add is our STT move to non-AI. And here we can see we have a field for the actor. That's going to be the actor that will be doing the moving. And then we have the move to location. Both of these we're going to need to populate in some way or another. The actor field is actually very easy to populate because StateTrees has a built-in way to supply this context variable into any task that we're running on it. That's simply going into our blueprint here for the task and going into the category and typing the word context. It's not case sensitive. It can be lowercase if you wanted to, but do make sure that there's no typos. And then when we compile this and go back, you'll see that, hey, it's now immediately populated with a binding to this context variable. And it even does that when you have like a different name. I just changed it to like FDSFS, some gibberish. It just does it based on the type. So if you have multiple things that are actor references, only one of them should be the context, because otherwise they're all going to be filled in with the actor context here. But we'll just call this actor because it's descriptive. Now, we have this move to location, and we can just manually say, hey, I want you to move to like 100, 500, 200 or something like that. And that will manually make it move that direction to that location. Of course, that's not what we want to do. We want to be able to do this dynamically. It should pick a location to move to and then move to that location. So you can just do that in here, of course. You can just calculate where you want to move to based on the current location and then like find a different location. And that is a fine way to do it. And that's probably the way to do it. But I want to show you how to set up a different task and access information from that task to populate the move to location variable. So let's make a find location task. So we'll make a new blueprint task, and we'll call this STT find location. And here we'll just make a variable which we'll call location, and we'll set this up as a vector, and we'll make a variable that we'll call radius, and we'll set that up as a float. Then on state enter, we also actually need the actor again. So let's make an actor reference. And just like we did before, we can set this to being context. And the wonderful thing actually is that if you set this up to be context, you don't even need to like expose it technically. It'll just do that for you. But let's just expose everything anyway. So we get that actor's location, and we get a random reachable point in radius. So the origin position will be the actor's location, the radius will be the radius, and then the location that we get out of that will be the value of our location variable here. And that's kind of everything there is to it. So we can now add that as a task here as well. So we can add that STT find location. I want to pull this up to above there. And now we can start populating these things. So this radius, we made a parameter for, so we can bind that to that parameter with this icon over here. If you press that, you can get any value that exists on the actor that we have. And the nice thing about that is because we have this drop down here for the context actor class, we can actually set that to our state tree character that we have made. And if we have any variables on there, we can actually sample from that as well. So let's make one just as an example. Let's make a like test var float or something like that. We'll make that a float so that it's actually like the right type. And if we now go to radius, we can on our actor find the test var float because we have set this up to use the context actor class of our state tree character. If we just go back to being a normal actor, we'll see that that actually is no longer available because it doesn't know what type of actor. So it's kind of like a built-in casting method. For our users, of course, we don't really need that variable to be accessible, so keeping this as generic as possible is a good thing, so that we can reuse this on other characters as well. We instead just want to bind to the parameter for walking distance. Now, this location we don't need to bind anything to, because this is going to be a thing that we set. Instead, what we want to do is we want to get our move to location on our move to non-AI, and we can then bind that to a value on a different task on this state, or any of its parent states. So if we put the location finding thing on the root here, I can actually show you that. Find location. We will be able to see that in the move to non-AI, if we want to bind something, we can get either one of these. At this point, I'm not sure which one is which though, so I'm going to delete this one again, because we're going to just do it on the same state. Or you can individually like bind the X, Y, and Z to floats and all that kind of stuff, as you can pretty much anywhere with any vector. So let's bind this, and now this is going to, when we move to location, going to look at whatever value exists on this task, which ideally will have run before and have picked a location. But this is a little messy still, because we still have these fields that we can manually fill in, and it's kind of weird. And what if we forget to put in the radius? Well, context isn't the only category that we can use to make our lives a little bit easier. If we go back into any of our tasks, we can set this location, which we are setting, to be an output value. That will get rid of all of the input fields, so it's only a value that we're setting through code, and we can then bind to. So we simply do that by going into the category and typing output. Again, make sure that you don't have any typos in it. And if we do that, we can see our location is now set as an output property. We will set that value, and then other things can bind to that value, which is quite nice. And that should even work dynamically. So if we're setting this in event tick based on like a bunch of calculation, a bunch of other data or whatever, once we update this, anything bound to it will also then reflect that with its like new updated value, because that is what a binding does. It's constantly checking that value. As for the radius here, we can set that up to be an input. And all that an input is that will, in the category, of course, that will just force you to bind it to something. It gets rid of the input field, so you can't manually put in a value anymore, but you have to bind it to something. If I remove this binding and I try to compile this now, it's going to scream at me that this input doesn't have a binding. So this prevents you from accidentally making something that will break your entire state tree. So this move to location on the STT move to non-AI, which is this one, probably also should be set to being an input value, because we always need to have something to walk to. And with this setup, we should now have something that pretty much just picks a location and moves to that location. So let's test that out. If we run this, we don't have a nav mesh yet, so it's not going to do anything. So let's do a nav mesh bounce volume. I will make that as big as it needs to be. Press P to check the nav mesh that's been generated. That's pretty good. And now we will see that he's just moving all over the place, because he's not waiting, he's not resting, he's not doing anything. He's just moving to a place, picking a new position, moving to that place, picking a new position, and just keeping that up. He also doesn't seem to be playing animations, but that's not the biggest issue right now. But our two tasks that we made are working together. This one is sampling from this one, and then when it finishes, it marks this state as completed, which by default then goes into the transition that we have set up for it, which is no transitions that we have set up yet, because that's going to be a video in and of to itself. So default transition is just going back to root, which means that it's doing just this as a loop right now. Now, I will say, you might think, okay, so then I can put a delay in here for like 1 second, or like even like 5 seconds. Let's make it 10 seconds. And then after it reaches this point, it's going to do this delay task and wait for 10 seconds, right? That's how that works, right? Well, no. Because as I said, when any of the tasks on a state finish, that counts as the state being finished. So when it moves to a location and it reaches that location, it marks the state as being finished and then does the transition. So what happens here is it either finishes on move or after 10 seconds. Whichever one of these tasks marks itself as being finished first will just trigger the entire state to be finished. So if I set this to 0.1, you will see that he gets very weird, because he's finishing the state every 0.1 seconds and getting a new position to move to every 0.1 seconds. And even if we delete this and I give this thing a child state, which we can now start playing around with, and we call this wait, and I put in a task for it to delay and say that's 0.1, it will do the same thing. So because this state is active, its parent state is also active, so it's still going to be doing the moving thing, but whenever this state finishes, it's going to go back to root and restart the entire thing. So this will still behave the exact same way. Even though we're technically like in the wait task, the wait task is part of the state that does the movement, so it's still going to be doing the movement as well. And if I set this again to 10 seconds, it's not going to wait for like this to be finished, because this is going to finish sooner, and that's going to get you back to here as well, I think. As you can see, whenever it finishes moving, it doesn't wait the full 10 seconds, it just does the thing. Now that's a little bit confusing because it doesn't actually show the transition here anymore, but it still does that. When something doesn't have a transition, it goes back to root upon finishing of any of the tasks in the state. Which is also why this find location task that we made doesn't finish anything, because it doesn't need to. It shouldn't, as a matter of fact. This just needs to set the thing and then be ready for anything else to grab that value. It doesn't need to tell anything that it's finished, because if it did that, we would never be moving. I can actually just show you that by adding here the finished task. And now it finishes every frame, which is a little wacky, isn't it? The whole finish task thing, again, is a little counterintuitive, but this is how like hierarchically that works. And that's the basic rundown of tasks, inputs, outputs, context variables, and all that kind of good stuff. So combining this with what we're going to be talking about next, which will be transitions and enter conditions, then we can start making some really, really interesting stuff. So we have this AI that is just kind of running around minding its own business, but it's not standing still at any point, it's not doing anything else at any point, it's just kind of running about aimlessly, which is maybe less than ideal. So let's give it a state where it can rest every once in a while, right? So we have this state tree that we have set up so far, where we do patrolling, and then we had this wait task, and we tried to do that as a child, but hey, that didn't work, because that's not how these things are like structured. That's just not how they work. Instead, this wait task needs to be its own state. It needs to go from patrol, which will change from being named patrol to being named like move to, instead, to be more descriptive, to going into the wait task. So these are going to be siblings instead of a parent and a child. So when we enter root, it's going to move to, and then it's going to wait, and then it's going to go through root again, move to, wait, and so on and so forth. From there, we can build up some other stuff. So let's set this delay task to being a little bit less than 10 seconds. Let's make it 5 seconds instead, and we can give it a little bit of random deviation of like 1 second, so it's between 4 and 6 seconds instead. We could even set this to run forever, so it's going to be waiting until it is forcefully transitioned into another state. But timing is actually exactly what we want to do. And again, you can bind these to outputs from other tasks, or to parameters, or whatever we want, really. So setting this up is actually remarkably easy, because in the move to, we can just add in a transition. And here we have a couple of different things that we can do. We can trigger this when the state is completed. So whenever it is either failed or succeeded, we do this. We can say when the state succeeds, we move to whatever we're going to be transitioning to, or when the state fails. And if you remember correctly, we set up the move to task right here to be able to say, hey, this task is finished either successfully or unsuccessfully in a number of different scenarios, whether that is not having an AI controller or not being able to reach your destination. So we can say if the state succeeded, we can go into waiting, but if it has failed, we can do something else, like deleting this actor because it's clearly in a position where it just cannot move. Or maybe reset it back to its original position, or we can do a variety of different things depending on what you need, but this is a way that you can easily make it go into different paths depending on what's happened. We can also just do on tick, so every tick, every frame, check a certain condition, and we'll get into conditions in a moment, to see if we should transition. So if you, for instance, wanted to attack the player when it gets close enough to the player, you would check every tick. If you are close enough to the player, it has built-in stuff for that, so that's kind of cool. And then move into the attacking state when the condition is met. We can also do this on event, and this is kind of neat. We can externally from our other code, whatever might be happening there, we can send an event with a certain gameplay tag to this state tree, and if that happens to be sent while we're in this state, that will trigger this transition. That's actually kind of really cool. So for instance, if you're in a attacking state and you get damaged, you can send a event tag to make it go into a damaged state, make it go stunned or something like that. For now though, what we're going to do is just on state completed. Doesn't matter if we failed or succeeded or whatever. We're going to go transition to a new state. And we can transition either to none, which makes it just get stuck in this state. So it's probably not the best thing to do. The next state, so that's going to just go through and see whatever is beneath me. Like what is under me, I'm going to move into that one. Just to be clear though, this only counts for sibling states. So if I add a sibling state to the root here and put this one down here, it might seem like this is pointing to next, but since this is a state that is entirely unrelated to whatever this state is, it's like it's uncle, right? If these are siblings, this is the parent, this is an uncle state. It can't transition to its uncles or cousins or whatever stuff like that. It can only transition to siblings, which is exactly what we need for what we're doing right here. But let's just run down the list for the sake of showing everything. We can do the next selectable state. So this just next state will try to just move into explicitly what is under it. But if this has an entry condition, which we'll talk about in a moment, that makes it unable to be entered, this is just going to short out and effectively go back to root, is usually what happens. If you try to enter something that can't be entered, it effectively just resets the whole state tree. However, if you do next selectable state, it's going to effectively just kind of work as trying to select its children in order, but what it will do instead, it's going to try to select its siblings in order. So if it can't enter this waiting node for whatever reason, it's going to try to do whatever is under it. And if that's not possible, it's going to try to do whatever is under it until it runs out of siblings. Or we can just mark this as the entire tree having succeeded or failed, which, as you remember, is useful if you're using SubTrees or linked SubTree assets, because those will be able to communicate that way that, hey, the tree as a whole is now finished, and whatever tree has me running as a singular state can now move on, because that will trigger the on-state completed for whatever state that is in. I think I want to make a video specifically just diving into SubTrees and just setting up some SubTrees to actually show you how these work instead of just loosely explaining it, because I feel like that's going to make you understand it a lot better. But within the context of transitions, that is all you need to know for right now. So with all that, we now just have made a loop with a delay in it, effectively. So if we make sure that everything is compiled and saved, and we run this, now we see he runs, he waits, and then after a couple of seconds, he runs again, he waits, and that will repeat pretty much infinitely because we're just looping through over and over and over again. So let's make something that is a little bit more interesting than this. When we're waiting on state completed, I want to check, for instance, the distance to our player. And if it is within a certain range of our player, I want it to do one thing. And if it is not within that range, I will want it to do something else. At the end of our waiting task, let's add a transition. And here we can start adding conditions. We can make our own conditional checks in a moment as well. That's actually really interesting to do. But there's a lot of them that are just provided. We can just compare a bool variable, we can do a distance compare, enum compares, float compares, integer compares, or we can just give them a random chance. And this is the wonderful thing about state trees. It just has a built-in random chance. So we can say, hey, we want to give this like a 30% chance, so 0.3, to go into any like given state that we provided in with, which is kind of cool. And if you add multiple conditions at the same time, so we can do this and a distance compare, you can see that this has a little and on it. We can also change that to an or. So we can do, hey, if this randomness is true or the distance compare is true, this transition is now valid. Or they need to both be valid. So it need to be within a certain distance and have that random chance just roll in our favor. And we can add like a bunch more of these. Of course, we can then do this and this or this. Like these binary operators work the same way that they would for like branch now. It's like just normal Boolean stuff, right? So you can set this up however you want. For now though, we're just going to do this as a distance compare. And there we can get, hey, the operator. We want to get equal, less than equal, greater or equal, is true. It's kind of a weird one. So we want to check whether or not it's less than equal distance between two things. So the source is an input. And we should just be able to get the actual location, but it seems like since I'm using 5.4, this might be an older version which doesn't have that implemented yet. In newer versions, you have a built-in get actor location function here that you can use, and then you can give in an actor to get the location from. That does not seem to currently be working, which is actually the perfect chance for us to, instead of using a pre-made transition condition, to make one of our own. So let's make one that just literally checks the proximity to the player character. So we can just get blueprint class, and then type in condition, find the state tree condition blueprint base, and we'll call this STC for state tree condition, distance to player. And here we only have one overridable function, and that is receive test condition. In newer versions, you also have a function where you can override the text that it displays as a little explanation. Again, state trees are new enough to the point where it's actively being worked on. Some things are a little buggy sometimes, like writing to parameters as of right now. And it's constantly getting new features as well. I'm just using Unreal 5.4 for this series. My experience using it has been at 5.5, and I can already tell like there's differences in things that are missing in 5.4. Anyway, this receive test condition just gets us a bool that will either let us go through or not let us go through. So we need a couple of variables here. This will be the actor variable that we have in our context. So this will just be an actor reference, and we'll set that as category context. We'll use that. And then we'll also just get player character. You can also make this like a target input or something, and then like this, and make that a input and use that instead. But then you would need to supply that in, which actually, let's do that because that's a little bit more fun to do it that way. So we have our actor and our target, and we'll get the actor location from both of those. And we'll get the distance between those two vectors. Now, I want to do a select here. And we're going to be selecting based on a compare. And that will be of type eComparison-methods. So we do that, and then we get the equal to, not equal to, greater than or equal to, less than or equal to, greater than or less than. And we will return values based on all that. So we'll check the distance between the two. Is that equal to a inputs that we want to have? So that will be the distance will be a float. We can give that a default value of like 500 or something. So we'll check is it equal to, and we'll check is it not equal to, and so on and so forth. We'll just do this for every single one of these. So then we get greater than or equal to. So that's greater than or equal. I think you kind of get that point. So then we have the less than or equal, simply just greater than, and simply just less than. And if we hook all that up, now we have a condition check that we can reuse for like every single one of the comparison methods between the actor that is running the state tree and whatever its target that it is comparing against is. Also, do make sure to hook everything up. So now, in conditions, we suddenly have our custom distance to player. Well, that should probably be called distance to target, to be fair. And there we get the context actor in, and the target actor we can supply in through a variable. So now what we're going to do is, instead of just keeping this as context class for the normal actor, we'll actually change this finally to our state tree character, because we're going to make a variable on the state tree character for our target that we're going to be comparing to. So let's make this a actor reference. And with that, we can now say, hey, the target that we want to get is the context actor's target. And then it's going to bind to that variable. In the state tree actor for now, though, we can expose this to maybe make this editable on a per instance basis. But for the time being, I think what we're going to do is we're just going to set this to get player character after all. But this does make it more flexible, more reusable in different kind of scenarios to just make the task or make the condition check in this case, taking a variable. And then we'll check whether or not this is less than or equal to, I think 500 is a pretty good one. So if that is the case, what we're going to be doing is let's make a new state. So we can make the, let's say jump. I don't know what I'm doing, but it will jump. And after jumping, it goes back to root. Within that range, what we'll do is we will transition to the jumping state, and otherwise we just go back to root. So we'll try to do these transitions in order. So we don't need to set up an entire like inverse condition for this one or anything. Just for demonstration purposes, I guess, let's make a quick little jump task. So we can make this task, blueprint base, state tree task, jump. We will make an actor. That's going to be a context thing, obviously. Let's actually just make that a character right off the bat, because we're going to need that for jumping to be able to work. And when we enter this state, we get our actor, we jump. And then what we're going to do is we're going to just check inside of tick if our actor get movement, which all the way at the bottom is falling. And whenever it is no longer falling, that is when we will finish this task. And let's set this category to context. So now that we have that, we can add this jump task and transition on complete. We go back to root. That's actually just the default, so we can just keep that there. And now whenever you are within 500 units, it will jump before restarting. If we just let you walk around a bit, it doesn't jump at all. But if I am within 500 units of it when it stops waiting, it should jump before doing anything else. So we can just, there we go, and it runs away. So we effectively have it making a decision here based on some inputs that we give it. And we do this on state complete now, but what we can do instead is we can do this on state tick. So as long as it's waiting, whenever we get into 500 units, it immediately will jump and start moving again after that. So that can be like, we kind of scared it, and it's like, and start moving. So you can see it jumps and it starts moving again, and then it jumps and it starts moving again, because it's picking locations within 500 units every single time. But this makes it feel a little bit more reactive, because it's checking this on every tick. Now, ideally, what you would do is, instead of just moving back into move 2, maybe what you do is you run a query, an environment query. I have videos on that as well, to get a location far away from you and make it move to that location instead, and make like an entire like separate hierarchy for that, or like a separate couple of states. But those are transitions. That said, now that we have this condition made, these entry conditions kind of just work on the same principles, but except for being evaluated at the start. So when you try to enter a state, you can just put any condition that you want on here as well. So if a certain object is of a certain class, or if you have like certain gameplay tags on a container or whatever, it just checks, hey, is this check cleared before moving into the state? And if it is not, the state is considered unenterable, and it will deal with it as specified. So when trying to select children in order, when you cannot enter this state, it's going to try to enter this state instead. So let's say for this one, we can only make it move if the distance to player is greater than 500. And then the distance to player, we set that to player target. So now if we're within 500 units, it's never going to enter this. And all that is going to do is it's going to wait and jump again and wait and jump again and wait and jump again, which is a bit of a bad survival tactic, to be fair, but I don't know. Yeah, so it's going to just keep jumping because we have this set to on tick, actually. So that's maybe not ideal. Let's set that back to being state completed. But it works as expected, right? So it runs away, and then if we're within a certain radius, it will jump in a moment. But then it won't actually start moving again because it failed the entry condition of the walking state. And it will just wait and jump again, wait and jump again, pretty much infinitely. Now that we have this guy kind of wandering around and do its thing and responding to us somewhat intelligently, like when we're close to him, he jumps and then he just gets kind of stun-locked until we run away again, at which point he will resume his running around. It's not very intelligent, but it is artificial, so it is artificial, almost intelligence that we have made. Let's take a look at the state trees and a thing that I skipped over in the start, and that is evaluators and global tasks, because these things are kind of the same thing under two different names. They are both code that runs over the entire tree. So all these states, when we enter them, their tasks will run their enter task, and when we exit them, it will run the exit task. And then in the meantime, it can run a tick as long as a state is active. A global task is just something that does all that on the basis of an entire tree. So usually that is mostly something to do with updating information on tick. For instance, we have this distance to player check, right? Which we specifically coded to check our distance to a certain actor. But maybe we're using that in a bunch of different things. Maybe we're using that as a check. Maybe we're using that to decide things in certain tasks. That distance might just be a value that we want to be able to get easily in a bunch of different places. In which case, we can make a task for that and add that to our global tasks. And global tasks are just the same as any other task. So any task that you make can just be added in here as a global task. And every node or every state in your state tree has easy access to global tasks. So it's effectively just a task that is running on the root of your state tree, more or less. Except that, of course, you can have multiple roots. I can add a sibling to the root, and if I wanted to replicate what a global task can do, now both of these also then need to have a parent. So I need to add another sibling and then add both of these into there, and it becomes a little messy real quick. We can just do it with a global task and everything will just have easy access to that. So that's where global tasks come in. Now, evaluators are effectively the same thing, but they are tasks specifically made to run on entire trees. So if you have a task already that you're like, but I actually kind of just want to run that globally, you can make them into a global task, and that's kind of a good enough way to do it. If there's any code that is specifically going to be designed to be run on a tree as a whole, that's where you just make an evaluator for it instead. The reason that both exists is this is kind of just nice to be able to reuse some code that you might already have, and global tasks existed before evaluators, I believe. So evaluators are just kind of the new and improved version of global tasks. So let's make a evaluator here that will keep track of our origin position. So the position where we started, so that we can make our patrol not move away too far from that. We're going to make a patrol within a certain radius of its starting position instead of within a certain radius of its current position. I think that will be good to do. So to do that, we can simply go into our blueprint classes here and we can type evaluator and get the state tree evaluator blueprint base, and we call this something like STE, state tree evaluator. get start location. And this will be relatively straightforward to make. But we have three functions here: tree start, tree stop, and tick. So when the tree starts, we can do something. When the tree stops, we can do something. And we can, of course, do something on the tick as long as the tree is running. For this, of course, we want to just get our position when the tree starts. So we add a variable for our context actor. So that'll be actor of type context in the category. And then the actual type will be of type actor object reference. And we'll just get the actor location of that, and we'll promote that to a variable, and we'll call this location. And then in the category, we will mark this as an output. And that's kind of everything that this needs to do. This just will get and save our starting location so that we can use that easily throughout our state tree. So these things are kind of more how you get and set dynamic things. These evaluators will themselves set values based on maybe other bindings that they have, and then other tasks can read from the evaluators. So a lot of this might happen within like tick. And you can specifically optimize that to only tick when they get certain events, of course, so that they don't run constantly, like I showed you in, I believe, the previous video. So now that we have an evaluator, we can add it as the start location, and we can see that indeed it has a location out. So now if we go into the move to, we have this move to location. Instead of doing this and the find location, we'll actually change the find location, I think. So instead of taking in the actor context here, because we don't need that anymore, what we want to do is open up our find location, and we just make a origin variable that we set to being a vector, and that will be an input because it's always going to be required for this to work. And then we can get rid of this context because we don't really need that anymore. We just use this origin instead. And for this origin, we still can just use the actor's location if we wanted to. Again, I think that might not quite work in the current 5.4 version, but in 5.5 that does work. So here in move to, we have this origin, and we can bind that origin to anything on the character. So yeah, there's also in 5.5 and beyond, there's also just a like get actor location option whenever you want to bind a vector like this. So you will be able to do that. Doesn't seem to exist in 5.4. But instead what we do is we get the starting location from the evaluator that we made, and now it's going to always try to find something within 750 units of the starting location. So it's never going to get outside of like a circle that is, I don't know, about this big, which we can test by just doing this. So we can just stand here for a little while, and instead of walking even further away from its origin position now, it will just stay within a certain radius, which is quite nice. That is especially good if we start doing other like more complex stuff, right? Because we can do something where we can add a child state to this and call this patrol. And we can get rid of this jumping, because that was just for an example. Let's get rid of the transition to that as well. And then when we complete this state, we're just going to go immediately back to move to. We're not going to go back to root. And the reason that we do that is we're going to put these two within the patrol state instead, because we can add another sibling to the patrol, so another child to the root, and this will be chase, for which we will change the move to non-AI as well, and we'll also put in a goal actor here. So we'll just call that goal actor, and we'll change move to location to not be an input anymore, because it's no longer necessarily required, because we can do either this or this, and inputs always need to be filled in. So we can provide in an actor instead, and with that it effectively becomes a possible chase task as well. So within chase, we add a child state where we we move to, so that is move to non-AI, and we're going to be moving to the actor's target that we set up before. And it's just going to entirely ignore the move to location, because the move to actor or location will prioritize moving to actors. So when that is finished, what we want to do is we want to move on to the next state. And the next state, let's actually call this run to target. And when it is finished doing that, it will add a sibling state. We'll call this jump again, and it'll just do the jumping. Of course, this would be attacking in any reasonable video game, but we don't have any like combat setup for this example, of course. So we just add a task for jumping, which will then get us back to route, which will get us back to patrol. And then patrol is going to have a transition on it for on tick. It's going to check this every frame, as long as it's within patrol. It's going to try to move to chase under the condition that we have a distance to the player that is less than 500 units. But that's a one-way street, right? So if it is less than 500 units and I manage to get away from it for more than 500 units, it's still going to stay in the chase state until it is specifically told not to be in the chase state. So unless it gets to me or I set up something in the chase state to go back to patrolling. So let's set something up in the chase state to go back to patrolling. If the state is on tick, we transition back to patrol. This interface also looks better in 5.5. It actually just shows you a miniature version of this hierarchy instead of just a dumb list like this. So again, the system is being improved constantly. But the condition, let's check the distance to player. If it is greater than 1,000, we'll consider that having escaped. And we'll compare that to the target actor for both of those as well. So now what this will do is we will be in the patrol state, which will just move to, wait, move to, wait, move to, wait, until the player or its target gets within a certain radius, at which point it will go into chasing. It will run after us. And the whole reason that I'm setting this entire thing up is because when it goes back to patrol, it will go back to patrolling around its original location. So I can lure it away very far. And then when it loses interest in me, it's going to go back to its original position. It's not going to keep patrolling around the place that I lured it away to, which in a lot of cases, in a lot of games, would break AI and would do weird stuff. Most games have a concept of going back to an origin position for an AI when their task like resets to just patrolling. So we can see he's just patrolling, but when I get within a certain radius, he starts to run after me. But then when he gets to me, well, he will actually always be trying to get me now because I'm still within 500 units. So I think it is a good thing to add in a sibling set here as well to wait again. So instead of going back to route, I want this to transition to the next state on completion. So let's go next state. And then I will add in a delay for this one, or like 4 seconds with a random deviation, which can then go back to route to do its entire thing. So let's make it chase us, which is kind of annoying to get it away from its origin position now that it is going to wait every single time. But I'm just trying to lure it away from its origin position so that you can see that when it resets and goes back to patrolling, it will go back to patrolling within its like original range. It's not going to just start patrolling around its new position. So as you can see, it runs back to roughly where it started within about 750 units. So that's where things like these evaluators can come in really handy. And again, we can also fairly easily just make an evaluator to like state tree evaluator, get distance to target. This might be useful information for a bunch of different things, right? So we can pretty much just copy a bunch of the stuff like from distance to player, like effectively this entire setup. We can just do that on tick and we promote this to a variable. Call it distance, make it an output, and that's kind of everything there is to it. We do need to also make these two into variables. The actor, of course, will be then of type context. The target will be of type input because we're going to want to have that always filled in. But just like that, we now have an evaluator that will always have an up-to-date value for our distance. So we can go back into the state tree add that in as an evaluator. Get distance to target. We can set up the target to be the actor target variable. And then we have this as a usable, referenceable, is that a word? It is now, value that we can use anywhere in the state tree. So making these evaluators is kind of a workaround. Instead of using parameters dynamically, you can just make these as little calculations that take in stuff. Like these are taking in values, and these can even like take in parameters or take in things from other evaluators if need be. And then expose the value out for you to use in a bunch of other stuff. So now instead of using this condition for get distance to player, I can just change this fairly easily to a float compare. And I can just compare the get distance to target distance to a number. And I can check whether or not that is less than or equal to. And now I can reference that number from a bunch of different places. Everything we did here also technically is possible to do within a global task, but since these are things that are very much just only useful to do within like the context of an entire tree, there's no real use making them into a task, and making them into an evaluator is just a little bit smoother, a little bit better. So I think in the next video, what we'll do is we'll make an evaluator that creates a cooldown. Because one of the things that state trees at the time of recording this anyway, is missing, that behavior trees do have, is the ability to add cooldowns to certain states, which I think is a bit of an oversight that might get added in the future. So that video might become irrelevant at some point. So we have some fairly simple state tree behavior for our character now. We are using a bunch of different states with tasks and evaluators and values and a lot of different stuff. But there's one thing that is a little bit lacking with state trees compared to behavior trees, and that is that there's no real way to put an entry condition with a cooldown on it. You can't say, hey, keep this entry condition locked for X amount of time after it has been initially entered. And I kind of just want to set up a fairly basic way around that, honestly. This will require you to have a specific context actor class that has some variables set up to work with this, just due to the sheer fact that we need to access a variable that we're going to be making on this class. And that's a variable that we can't send through as a reference. We need to access it directly. So let's make that. And what we're going to be doing is we're going to be making a new variable, and I'll call this cooldowns. And I'm going to make that of type name or string. Let's just do string for now. I think name technically performs a little bit better, but it's not that important. And we're going to make it a map. And it will have values of float. So it's going to be a string and float map. Then we're going to make a condition to use that. So what we'll do is we'll make a state tree condition, and we'll call this stc cooldown. And the annoying thing about state tree conditions is that they are read-only blueprints. You can't set variables within this, but maps are actually kind of a special thing because you can edit them from a read-only blueprint. So we can do our test receive condition, and we'll make a variable for our actor. And we're going to make that specifically of our type state tree character because of the map that we made on that. It's going to be the context variable because we just want to automatically provide that in. And with that, we can now get our cooldowns, and we can check if we can find a certain cooldown. And this is going to be a variable as well. So cooldown name. We'll just make that a editable field. If we can't find any cooldown, that means that we have no cooldown on that name. Like we haven't entered that cooldown yet. So that's what this bottom pin is telling us whether or not it could find that. If it could not find that, we just add it as a new one. So we add to it our cooldown name, and we're going to be adding that with the current game time in seconds, plus an amount of cooldown time. So this is a cooldown that starts from the moment you enter this state. From the moment you first check it, if you pass the cooldown, it's going to immediately start ticking down. It's not a cooldown that necessarily will start ticking down from when you exit the state and you have finished a task. We can make a task to do that though in a moment, which we will do. But by default, if you're just using this condition, it will only work from entry of the state. Or I suppose it will work on exit if you use this condition as an exit condition for a transition, but that would be kind of weird. Anyway, we're going to promote this to a variable, and this will be the cooldown time, which also will be exposed. So if we don't already have it, we add it in, and then we return true. If we do already have it, we just want to check, hey, is this less than our game time? And we just add in a branch for that as well. Because if it is, that means that the cooldown has been there long enough, and we are allowed to enter this again now. So if it is, we just add it again. If you add a thing into a map that already exists with that like key, in this case the name, it will just override it. So we can just use the adding node here in both scenarios, and that will just update the time for it. But if this has not in fact returned true, so if our cooldown is not less than our game time in seconds, we return false. So we just untick this and we return false. So now we have a condition that effectively checks whether or not a certain actor has a certain cooldown, almost in a tag-like system. So we can say, instead of doing a waiting task here for chase, we can do this as an entry condition now. And we can say, hey, cooldown. We can say the cooldown name is chase. And the cooldown time is, I was going to do 15 seconds, but then I mistyped and now it's 14 seconds. So short, which also means that the jump now doesn't have anywhere to go actually. So maybe that wasn't a great way to do it. We can just make the jump go back to a root. That's fine. So we just default transition. So now what this will do is when it starts chasing me, it adds that value to that map. And when it tries to chase me again, it will check whether or not the current game time has exceeded that like threshold time. And if it doesn't, it's just going to patrol. So now you'll be able to see that he does this thing, but when I get within a certain range, he comes close to me, and then he jumps, and then he waits for a moment, and then he'll start doing all this again, but he won't start chasing me again until his cooldown of, I think, 15 seconds, I changed it anyway, is all up, at which point he will start chasing me again. So he now has a cooldown on his chasing behavior. But what if we want to also make a task where we can say, hey, extend that cooldown now? Because right now we can only extend the cooldown if the cooldown has been passed, but maybe we want to be able to have a task that also extends the cooldown. So for instance, on finishing a certain state, we want to extend that cooldown. Well, that's super easy to do as well. So let's do that. We can make a task, blueprint task for stage 3 base, and call that STT set cooldown. And here we're just going to copy over a couple of things, actually. We're going to copy over the actor. We're going to copy over the cooldown name. We're going to copy over the cooldown time that we're going to be adding to it. So we can set this up in a handful of different ways. We can set it up to say, hey, reset the cooldown. So the cooldown will be X amount of seconds from now. Or we can set it up to add to the existing cooldown instead. I think we're just going to make a tick box that will let us decide what we do. So reset cooldown with time or something like that. So by default, it's going to be adding to it. But if we take this to be true, it will instead set the cooldown to be whatever we put in here. So that can also make it shorter as a result. So that can be quite interesting. You can set this up to be either on exit or on enter. I'm going to do this personally on exit because I think that makes the most sense for setting a cooldown. But you can do this on enter as well if you wanted to. So here we first and foremost check if the cooldown timer should be reset or if it should be added. And let's give these things a couple of categories. So we give this the category for context, for the actor itself, of course. And then these two don't need any categories. And with that, we can kind of just copy some stuff over here. So let's just copy over everything, and I will delete everything that we don't need. How about that? Because we need most of this. We still need the actor cooldowns. We need to check whether or not we can find it. Because if we cannot find it, no matter what happens, we need to just add it anew. So that's actually the first thing that we do before we even check whether or not we want to reset it. Because there's nothing to reset or to add if it doesn't exist yet. So if it doesn't exist yet, we add it. If it does exist, we check if we want to reset it or if we want to add to it. So if you want to reset it, what we do is we also just hook back up to this node. We don't really need this one or this one, because resetting effectively just means getting the current game time and adding to it our current cooldown time. And adding to it the amount of cooldown time that we want to do. So that's effectively the same thing as just setting up an entirely new value. But what we can do as well, we can use this adding node, hook everything up properly, like the cooldown name, and then we want to add a new amount of time to it. So from that, we're going to take the finding node that we have here and add to it the cooldown time instead. So if we're not resetting, that means that surely we must be adding. So we go to this one. That's everything there is to it. We don't need to finish task because this is running on exit anyway. And if you want to be able to like make that variable as well, we can call this like run on exit. Ideally, maybe make this like an enum instead to make it a little bit more clear. But for now, we'll just make this like run on exit, and then we do enter state as well. And we can just hook both of these up to like a branch like this and check run on exit. And if run on exit is true with exit or is false with enter, we do that. So now it can run on either enter or exit, depending on the value that this variable has. I'm going to set the default value for it to true though. And the same thing with reset cooldown time. I think I'm going to set the default value for that to true. Cooldown time, don't need a default value. So now we have a task that we can add into any state on our behavior tree that can run on enter or on exit, that will either add to or reset the target time for our cooldown as well. And that can actually work fairly interestingly, because we can say anytime that we enter the patrol state or the move to state, because we never actually re-enter the patrol state seemingly. So every time we enter the move to state, we can add this task here, which is set cooldown. Our cooldown name was chase. This is case sensitive, so it might be a good idea to make this into a parameter if you're going to be referencing it in multiple places. Or just copy paste it, but just making it a parameter is probably easier. Now it's the other one to chase. Yes, I did actually use the uppercase there. Still going to just copy it over just to be sure. And we can say the cooldown time is actually going to be -2. And we don't want to reset it. And we don't want to run on exit. We want to run on entry. So that means anytime it enters the move to state now, it's going to reduce our cooldown time by 2 seconds. Didn't see that coming, did you? But that is entirely possible. So this is now a task and a condition that can really work together fairly well. And they all just work based on these strings, or again, you can use name variables if you prefer. The only downside is that it is limited to using this actor context class, because we need to directly interface with that map. You might be saying, but you can make like an interface to get that map. Sadly, you cannot. If you're using C++, you might be able to, because you can actually get a pointer to that specific map. But if you use a interface function call in Blueprint, it's going to pass it through by value, meaning that it's going to give you a copy of the map. So you can't actually edit the original map through an interface call. You need to actually do it through getting the actual actor and getting the actual cooldown map from that actor, meaning that you do need to like effectively do that cast, right? So you're going to be stuck with having to use like this base class that has that variable on it. That's the only real downside to it. Just during editing, listening back to this, I wanted to cut in real quick to explain that you still can set this up to use an interface. What you would need to do is you would need to move pretty much all the code that we just took from the condition and or the task, and put it in the implementation of the interface on your various different classes that might need to work with these cooldowns and have their own maps. And then for the interface function that is going to be used for the condition, it just will return a Boolean variable, whether it's true or false, whether you can succeed or not. That way you can still use this on a bunch of different classes, and you can still make this fairly generic without them having to share a parent class, which might be an issue for a variety of reasons. It would be ideal if you could just have a cooldown functionality on these things provided by Epic itself. That is a little bit more like flexible. But just about every other method of checking this doesn't quite work, because if you just make it check that within the same condition, there's the issue that these conditions are objects in and of themselves, and when the state is no longer active, those get discarded, and when you re-enter the state, it creates new ones. Ideally, you would be able to use parameters instead, but setting parameters is a bit of an issue. Through C++, I think it is possible. Through Blueprint, it's a little bit iffy because it seems to work in editor if you want to set a parameter, but then when you package the game, it causes crashes, so don't do that. And we have a similar issue if you wanted to use an evaluator for this, because if you bind to these in a task that is trying to set stuff in them, it's going to pass them by value, not by reference, so you can't actually edit the original values on these evaluators. These are only for getting, you can't set these externally. This is one of those things where if you were using C++, it would be trivial to get a pointer reference to these, to actually be able to edit them. Blueprint makes it a little bit more difficult, so this is the way that I have found that works to set up cooldowns for state trees. So the project has been updated to Unreal 5.5 because I want to show you some things that have been very recently added as of me recording this. And the first and foremost important thing is the new selection method that we have. So if we go into a state tree, you might remember me going through the selection behavior of these nodes. So they choose what child state to run based on some selection behavior. There's a new one. And this one can let you select it based on a utility score or at random weighted by the utility scores. So let's talk about these selection utility scores, because they are added newly in 5.5 and they can really be used to make your state trees a lot more intelligent, a lot more easily. Of course, the state tree that we have here is relatively simple, so there isn't a lot of choosing to do. So most of this is going to be theoretical. So, how do these selection utilities work? They all have a weight and a couple of different selection methods, or a couple of different tests is the way you can think of it. So, just adjusting the weight doesn't really do anything because the weight is a multiplier for the score that they have. So, by default, they don't have any score. So, if I set this to try select by highest utility, and I just set this to a value of 2, for instance, it's not going to do anything because it's effectively just multiplying 0 by 2, which is still 0. And if it's a tie between them, it just does them in order. It does them in sequence, just like normal select children in order. So what we need to do is we need to add a constant for now. So if we set this just back to 1 for the time being, and we set this to 1 as well, this will now have a constant value, which is just a literal float value. You can bind this to anything you want, of course. Anything that is float or number adjacent. But for now, we just set this to a constant value of 1, which means that the weighting node now has a value of 1 with a weight of 1. The move to node doesn't have anything, so it's going to go into weighting. I've set the weighting node up to transition back to root, so it's always going to be skipping over the move to now. And we can see that because it has indeed stopped moving, but it will still chase me, but it doesn't patrol anymore because it's immediately going from root to waiting to root to waiting to root to waiting over and over again. But we can see if we put another constant in here and we also give that a value of 1, now they're tied again, which means that it will operate in order and it will have the patrolling functionality again. But if I then go back in and instead of changing this, which is just a 0 to 1 value, we change the weight of this to be 2, you will see that it goes back to immediately going into weight again, because they both have a score of 1, but this is getting multiplied by the weight of 2. So no longer does it walk all over the place again. Now, that doesn't really do much if it is a static value, because obviously you can just set up your transitions that way. This is good when working with dynamic values. So we can do like binding this to a HP percentage, for instance, so that it's less likely to chase us when it's low on HP. So we would make this root, instead of try to select children in order, we would make this try to select children in highest utility. And we would put a utility thing on here that would represent our enemy's HP on a 0 to 1 scale. Now we can even use a utility selection for the distance to our target. So in this chase, what we can do, we can maybe make 2 different types of chases. We can make one that runs toward the player and one that runs away from the player with like an environment query, right? So what we would do is we would just add a child state to this and put all of these inside of that child state and call this run to player, or run to target more accurately. And then we could add a sibling state to this, and this would be run away. And this could do the running away. So when we chase the player, it doesn't really matter, because chasing the player is more like sensing the player. The player is nearby. Do we run after the player or do we run away from the player? So we can do that based on selection utility. If we have a evaluator here that would have a float value of our HP percentage. So on a 0 to 1 scale, do we have 50% HP? That would 0.5. Do we have 10% HP? That would be 0.1, and so on and so forth. But that is just with constant values. We can actually interpret values as a float input instead and be a little bit more flexible with them. So what we can do is we can use a response curve that takes an input range and that normalizes to 0 to 1. So this might be good for a thing like doing things based on distance, because your distance value is going to be in the hundreds or in the thousands of units. But to make them easier to work with, you can say, okay, we're going to normalize this from 0 to 3000, and that's then going to normalize down to a 0 to 1 scale that you can more easily use in this curve. So we can say at 0 units, we actually have a value of 1. So it is going to be weighted fairly highly. It's going to score fairly highly because it is really close to you, which means that it needs to attack or it needs to do something. But at a value of 1, which we can do by just adding another key curve, time is 1, and then the value will be 0. Of course, this is just a linear line. You can add in however many more points you want to make this shaped the way you want, or you can even use a curve asset, like any curve asset that you have made. You can just put in here and it will show up as that curve, which allows you to have a little bit more control over the fall off and the tangents of your points. And theoretically, you should be able to even output a value of bigger than 1 on this. I don't think in most situations you really want to do that, but I don't see any reason that you couldn't. If you make a curve that goes up to a value of 2 or 3 or 5, you would just have a bigger value being outputted by this specific test. So here what we could do is we could have that inverse linear curve that we had a moment ago. So at time 0, we have the value of 1, and then at time 1, we have the value of 0. It's not quite a linear curve anymore at this point because it has these tangents working for it. But that means that if we have full HP, this is going to return a value of 0. So it's not going to be weighted very highly at all. But if we have almost no HP at all, it's going to be a lot more. It's going to be valued a lot higher. So if we put that test on here, it will run to the player when it's on high HP. And if we put an inverse of that on the run away state, what it will do is it will score higher as your HP lowers, which at some point is going to intersect and is going to make it so that it doesn't run toward the player anymore, but it runs away from the player based on those dynamic inputs. Now, of course, To make it a little less predictable and a little less mechanical, what you can do is instead of doing just by the highest utility, you can select them at random based on a weighted utility. So that will just turn the utilities instead of a pure selection method of saying this has 2 and this has 1 as its score, so we're going to always go with this one. What it does is it normalizes those values. And it says, well, this one has twice the value of this one. So out of 100 times that we're running this one is going to show up twice as often as this one. So that would be a 2 to 1 ratio. So out of 3 times that we run this, it's going to do this 2 times on average, of course. It can very much do it 10 times in a row because that's just how statistics work. And it's going to do this 1 times out of 3 on average. And then the last one that we have is a enum input. And this one is actually very, very interesting because we can choose what type of enum we're using. The default will be the state tree any enum, which doesn't really do anything. But we can take any variable that is an enum on our available bindings. In this case, let's say we have the auto-possess player enum. And we can say, well, when it's auto-possessing player 0, we give it a value of 1. But when this thing is set to auto-possess player 1, we give it a value of 0.6 or something like that, right? For the auto-possess, that doesn't make a lot of sense, admittedly. So realistically, you would have your own enum. So we can do something like just making a quick enum here for that. And let's call this aggression state, just to keep with the example of attacking or running away from the player. And we can add an enumerator to this, and we can say this guy is angry, or this guy is neutral, or this guy is scared, or anything in between. You can add as many states to this as you really would like, because again, that's just how enums work. Then we can add that to our state tree character here. So we add our emotional state or something like that. We'll call it emotion. And we call that the aggression state. So now that we've added that, we can use that on here. So we have the emotion variable. And we can say, well, while you're angry, you're going to not run away. So if you're angry, you're going to score 0 on this because you're going to be confrontational. If you are neutral, let's say that we just score this at 0.5. But if you are scared, we're going to score this at, for instance, 1. And then, of course, run 2 player would have potentially the exact opposite. So we can use a enum input here, look at the emotion, and add 3 options to that. When you're angry, definitely we want to run toward you. When we're neutral, we want it to weigh a little bit toward running to the player. So you can either just put this at 0.5 so that it's a tie, or maybe at 0.6 so that it outweighs it a little bit. If you're doing this just based on highest score, this is a good way to make sure that this is picked before this when you're at neutral. But in this case, putting them both at 0.5 would do that as well, because when you pick them based on a score, again, if scores are tied, what it does is it just executes them in order, or it picks them in order rather. And yeah, when we're scared, we will set this to 0. Just keep it at where it is. So that would, now when we have some code that runs this emotion and sets it to its proper value, which we could just do as an evaluator or a global task on the state tree itself as well. It will now make different decisions based on that because we can use this selection utility for all that. As a little side note, because we're in 5.5 anyway now, we can also now more easily map vector variables on here. So we have this move to state that I made, and this has the move to non-AI, which takes in a move to location. In 5.4, which most of this series has been made in, this wasn't available yet, but now when we have a bindable vector parameter anywhere, we can use the getActorLocation function for that, which allows us to put in an actor or like bind any actor. So we can just move to, for instance, the target location or whatever. Of course, we didn't program this task to work with that, so it's like find the way it works. But for things like distance comparing, that can actually be really quite useful, because you can now set up a transition with a condition for a distance compare. And you can just set both of these to get an actor location, and this can just get the actor itself, and then this can get the actor target that we created and check if it is within a certain distance. So what we made an entire condition check for in the previous part or the part before that now is much easier to do with just the default handed tools. So that's a nice little update in Unreal 5.5 for state trees that you're really going to want to have. Most of the project files for this series are still going to be 5.4, so it's going to be a little confusing for anybody following along project by project, because suddenly you'll have to use Unreal 5.5 for this one. I'm sorry about that, but again, this is actively being improved and developed still by Epic, so features are still being added. So while we have an AI that can wander around and even when we get close enough chase us, and we've even discussed things to make him more responsive and dynamically responsive with things like utility scoring, we are going to run into an issue at some point, which we haven't really run into yet, but this is going to start to spiral out of control in size and become quite annoying to manage as this tree keeps growing and growing and growing. And then as well is we have pretty generic behavior in this tree so far, don't we? We have a simple patrol functionality that likely a lot of different state trees across a game would be able to use. So are we really going to like copy paste this into everywhere, and then when we want to change something, do we need to go into every single one of those state trees to update that code? That seems like not a great way to do it. The same thing with chasing the player. We can take away a couple of things that we did in the last video, but that also seems like maybe we should make it a little bit more reusable. Effectively, what we want is we want this entire state tree to just be the patrol state and the chase state, which both reuse modularly placeable code. So that's exactly what we're going to do, because I finally want to talk about linked assets. I talked about them a little bit in the first video. Talked about the difference between subtrees and linked assets, and how linked assets are effectively just a more organized way to deal with subtrees. So we're going to effectively never use the actual subtree type, just use linked assets. So let's make a couple of assets to link, shall we? I'm just going to keep the state tree here as the main one, and I'm going to copy it over, and I'm going to call this patrol. And I'm going to copy it over again, and we're going to call this chase target. So if I now open up the patrol state tree, it's going to be the exact same thing. We can throw out everything to do with chasing, because this is only going to do the patrol routine. We don't need this root state anymore either, so we can take this patrol and put it up at the top and get rid of the original root. This is only going to be, hey, we're going to patrol, we're going to move to, we're going to wait, and this in and of itself loops, which is potentially okay to do, because in our state tree itself, we have transitions that can cancel out of the patrol state. For the sake of making this video and teaching you something, we're going to change that as well. So first and foremost, we're trying to transition from patrol to chase anymore, which doesn't exist anymore. So we can delete this transition, because that transition is going to be handled within the state tree itself. And here we just try to select children at order, and we can get rid of all of the selection utilities that we made in the last video on both of these. And now wait tries to go back to root, which obviously doesn't exist anymore. So what we can do is we can either make this go back to the patrol state. And as you can see, by the way, I'm now in 5.5, and this little drop-down menu is a lot more readable. It's actually so much improved. But we can go back to patrol, which will make this loop. So when we enter the state in our actual state tree, it will loop until this transition happens and we go to a different state. That is realistically probably what we want to do. But alternatively, what we can do is we can finish the state tree. That's a concept that we haven't really discussed yet this far. State trees have this concept of being finished. And if it's just the main state tree that you're running on anything at all, when you finish the state tree, it's just going to actually finish. It's going to stop running and it will have done its thing. Unlike a behavior tree, which you can force to stop from externally, but they're not really meant to be ended. They're meant to continuously just keep running. State trees have built-in functionality to stop. And that mostly comes in useful with these sub-state trees, because when a sub-state tree, or a linked asset, as we call them, marks itself as being completed, that is then seen as the completion of the state within the parent state tree. So on patrol, after we finish waiting, instead of transitioning to the patrol base state again, what we're going to do is we're going to set this tree as having succeeded. We can also set it to having failed, and that will then count as specifically the state having either succeeded or failed, which we can use for transition information as well. In this case, we just care about it having completed at all, so it doesn't really matter. So we're going to mark this as succeeded. Now, let's go back into our main state tree, and I'm going to remove effectively everything. So we're going to remove this, and we're going to remove this and this, so that we only have the patrol state and the chase state left. This is all that this main state tree is going to be, and it's going to use these other assets for the actual behaviors, so that when this enemy starts becoming more and more complex, the main state tree itself is still nice and readable. Of course, the downside to doing this, I should point out, is that where before we had the possibility of going from any state within our patrol sequence to any other state in our entire state tree, that no longer is possible between different assets, of course. But since these states only really need to change between patrol as a whole or chase as a whole, we don't need to move from move to immediately, explicitly, exactly into jumping, which would be attacking if I had an attacking animation. So it's not that big a deal, but there might be reasons that you don't want to section off certain things into their own separate assets, because it does make going from specifically one state to specifically another state sometimes a little bit more difficult to deal with. But it also makes everything a lot more reusable, which is usually a good thing. So let's change this from just a normal state to being a linked asset, and then the linked asset that we're going to link to this will be the patrol asset. You can see that it has the parameters that we set up on this thing because we just copied it over. We actually just want to bind this to the parameter for walk distance that we have on the main tree so that it forwards it to still work properly. And that's pretty much everything there is to it. So let's also set up the chase target, which again, we don't need anything to do with the patrol. We can just move chase to be the new route, get rid of the original route. And then after we finish up waiting, we can add a transition to mark this as the tree having succeeded. Now, if you remember correctly, this run to target uses a move to non-AI. If we open it up in the editor, we can see that we have a couple of different situations where the finish task actually finishes as a non-success. So in this case, what we could do is if this fails at all, we can set up a transition on state failed. We set that up as the first thing. We can say that the tree as a whole failed, so that it doesn't jump and it doesn't do the waiting. Just when it fails running, it's going to stop this tree altogether, and it's going to mark that as having failed, just in case whatever is running this tree cares about it having succeeded or failed. And of course, in the chase state itself, we have this transition to patrol, which no longer is needed in the sub asset. So with that, we can change this all around, and this should work now. And we can go into the state tree itself that we're working with on the character, and chase will now also become a linked asset. Of course, that'll be the chase target asset. This one doesn't need a walk distance though, so we can actually go back in here real quick and just remove this as a thing. This thing also doesn't need to get starting location, so we don't need to like double check that. And I don't know if this thing at any point uses the distance to target. I think it might, but it probably doesn't. Either way, it's probably better to forward that as a parameter. So we might as well delete that too. Now in the patrol state, now that I think about it actually, we probably don't want to generate get start location on this, because this will generate a get start location every single time this subtree runs, meaning that it's going to get its origin position at the position that it is whenever we enter this state. We want that origin position to be provided from the start of when the parent tree, this one, the actual state tree that we're running, starts. So this will use the get start location. This one doesn't need that at all either. And I don't think like we're using the distance to target thing anywhere at all. So we can just get rid of that. But we can add a new parameter, which will be a vector to the patrolling state. And the name for that will be origin location, something like that. And then in the find location task, we can set our origin to be our parameter origin location. Going back into the state tree. Now, if we go back to patrol, we'll see that we also have this origin location as a parameter now. And we can bind that to our get start location from our evaluators on our main tree. So we're forwarding this information from our main tree to only the subtrees that require it. And we also really don't need this enter condition for the cooldown anymore on the chase target, now that I think about it. So let's remove that as well, because that cooldown also still exists on the state tree itself, the parent one. So you don't need to double up on that, because that will actually mess things up. Because when it enters this, it's going to set a new cooldown. And then when it would enter this, it would check the cooldown again and not run and get stuck. So yeah, do make sure that if you're like copying stuff over like this, you remove unneeded transitions, because they can actually like double up and conflict with each other. But now that we have all that, we effectively have the exact same thing happening here that we did before, except that it doesn't wait anymore, because I guess technically when it jumps, it also aborts this movement. So it sees this as having failed. So I think we just want to get rid of this. But aside from that, like little quirky difference, we have exactly the same AI now that we did before. We did a bunch of work to get back to the same point and added nothing new. But the upside of all of this is, number one, a little bit more readability, as I said before, because the actual state tree on the character now only has 2 states. And if we want to go into those states themselves also only have 2 or 3 states themselves. Matter of fact, this can just kind of get rid of the top one as well to make them even easier to deal with. And now if we make a different state tree that has like more other stuff aside from this, or maybe only uses the patrol and then has some entirely different behavior instead of chase, or the other way around, maybe something that only chases and doesn't really need to do a like idle patrolling or whatever, we can reuse this stuff. And then if we decide that actually we want to make this a little bit more intelligent, instead of just move to wait, we only have to do it in this one place, and then everything that uses this linked asset will instantly reflect that with updated behavior. There's one more concept that I really want to talk about the state trees, and that is the event. So you can see in 5.5, there's been a change here as well. The entry conditions can require an event to enter. We're not going to really look at that too much. As a matter of fact, I'm actually going to get rid of this distance to player entry event, or entry condition, rather. We're going to just do this based on normal transitions. Just know that these entry conditions can also use events, meaning that when you're trying to enter this, a certain event needs to be happening. But the use case for that is a lot more niche. So, what are events? Well, events are just messages that you can send to your state tree from other places of your code to tell it to do certain things, or more specifically, to tell it something has happened, and the state tree can then interpret that based on tags to decide whether or not certain states care about it, and if that is even like an active state or whatever, and deal with it as you set it up to. So what we're going to do is I'm going to go into the state tree proper, so the thing that has both the patrol and the chase state, and we're going to change this from, instead of just using onTick, transitioning to chase if the distance to the target is less than a certain amount, which is just a little goofy, because if you sneak up behind them, they won't see me, but they will still start chasing me. So what we'll do is we'll get rid of this, and what we'll do, and instead we're going to do this on event. We don't need to really use this condition anymore, and we can set this to have a required event. So we can make a tag specifically for this. This uses the gameplay tag system, and we're going to add a tag named event.scene, because we're going to be using Unreal's built-in perception system for this. We can set this just to the gameplay tags default.ini, add a new tag, and now we have event.scene. So whenever this state is active and this state tree gets a event.scene event sent to it, this transition will now happen. We can set up a certain payload struct to also send through certain information, and it has a bunch of different ones. So if I select a rotator, it sends through the XYZ rotation. So you can see that you can send through like fairly arbitrary data. I don't think you can easily send through custom structs with this, as far as I have tested. So that's not exactly ideal. I'm sure that it's possible to set up within C++ though, but there's a bunch of stuff that you can send through. So if you need to send through some information with your event, that is likely possible. But for the most part, I just use these to update that an event has happened, and usually that doesn't really require sending through information necessarily. At which point we can just transition to something. We can set up a priority, because you can send multiple events to a component like this. If multiple of these transitions were to trigger at the same time, these priorities will say, hey, if you're a higher priority than something else that's being triggered in the same instance, go with the thing with your higher priority. We can even delay the transition. So if we, for instance, see the player, we can say, well, wait about a second until you actually start going into the chase, just to give the player a little bit of a head start, that kind of stuff. We're not going to do that, but you could do that. So then on the chase, what we'll do is, instead of checking again the distance to player being bigger than a certain amount, we'll just say, hey, if you cannot see the player anymore, go back to your patrol. So it'll also be a little bit easier to get rid of a chasing enemy, because if I run around a wall, for instance, it'll just stop seeing me. Now, in an ideal world, what you would do is you would still make it move to your last known location. And if it can't pick up seeing you within that little last portion of the chase, then it would go back to patrolling. But for now, I just want to show you how these events work, and not exactly how to like set up a more advanced, like more intelligent chase routine. So we're going to ignore that part of it for now. We just want to focus on the transition events. So let's set up that event, and we can make a new tag in here and call that event unseen. You could technically just use the same tag for this. I like sending through a different tag to prevent any confusion, any possible mistakes happening. And having like one more tag in your project doesn't really hurt. Like, tags are pretty cheap. So, and then we just make sure that we mark this with the proper tag, which after making the tag, sometimes I forget to actually mark it with that tag, so don't forget to do that. And now when we get an event with unseen, I will go back to patrol. So let's send it these events, shall we? Because that's quite important. And the way we will do that is by making an AI controller class, because I don't think we have one of those yet. So let's make an AI controller. And admittedly, if we were using an AI controller state tree, this would be a little bit easier to accomplish, but let's make it so that we can send this through with the character instead, because I still really like the idea of having the state trees predominantly be on the characters themselves. So we make an AI controller, and we'll call this AIC, I'll just call it AIC BP, AI controller blueprint, on which I'm going to put a perception component. On that, I'm going to set up the sense of sight, AI sight config, and we'll just kind of keep with the default settings, I think. So it has a 90-degree view cone, loose side radius is 3,500 units, side radius is 3,000 units, We can detect enemies, neutrals, and friendlies in this case, because we don't really have like an alliance system set up. That's another sense that we can set up if we want to, but that's not what this series is about, so we're just gonna make it sense everything, and that's pretty much it. So let's go into the event graph. With the AI perception selected, we can say on perception updated, which gets you an array of every actor that its perception has been updated with. Alternatively, what you can do is just on target perception updated, which will get you a singular actor, which is just a little bit easier to work with. Because all we need to do is we're going to need to check if that actor is equal to our get pawn. So that function is called get controlled pawn, which we'll need to cast to our state tree character, because that has on it a target variable that we made a while ago. So we want to check, hey, did the thing that just updated our perception match the thing that we're supposed to be looking out for? Before anybody complains about casting, since this is always going to be running on a state tree character anyway, this doesn't cost anything because everything is loaded into memory regardless. So if the thing that just updated our perception is in fact the target that we're supposed to be looking out for, we're going to break the stimulus so that we can see the stimulus location. This is what you would use if you wanted to set the last known location of your character and make it move to there and like do some more fancy stuff. All that we care about at the moment is just whether or not it was successfully sensed. So we add in a branch, and if it was successfully sensed, what we do is we get the state tree component and we send, and the event we can split into its tag, its payload, in case you want to send through some information. The way you would do that is you can make an instance struct which has a wildcard, so you could like set up the stimulus location and make it send that through in this way. Again, I don't really care for that right now, but that's the thing that you could do. If it is successfully sensed, meaning that we're now within its field of view, we're going to send through event.scene. And if it was a false, that means that our new updated perception of that actor is that we can no longer see them. So that means that we're going to send through an event.unseen instead on the perception being false. Which again, you can send through that payload if you want, but I don't care. Now we do need to go into our character real quick, because the AI perception component can only see things that are set up to interact with it. So we need a perception stimuli source. And here we need to say we register this as a sense on the site. And I think you want to set auto register as source to being true. Otherwise you need to, I believe, explicitly like turn on the senses. So you'll be able to see that it starts chasing me now. But as soon as I go around like a corner where it cannot see me anymore, it's going to start losing interest and stop chasing me. And then it just goes back to patrolling. In much the same way, as long as I like stay behind it, there's going to be no chasing happening either, because it's actually relying on Unreal's sensing system, which has like a system for field of view, all that kind of stuff. So it's a lot more intelligent now, working with this stuff for perception. And we can use the transition events to make use of that. So these transition events can be really, really powerful in a lot of ways. And the AI is kind of freaking out because it could see me, but had no idea how to reach me. So that's kind of funny. So there's a quick little addition to round out everything about state trees. There's always more to learn. There's always more to do. These things can be used for so much more than just AI as well. You could use them for dialogue trees. You could use them for quest progression system, which I have an entire like custom quest system already up on this channel. I might redo a quest system and actually also a dialogue system. I might redo both of those in the future using state trees, because they are such a powerful and flexible tool to use for so many different things. They're a little bit less flexible than making your entire custom system from the ground up in a lot of ways, but they're also a lot more user-friendly and have a lower barrier to entry once you actually start understanding state trees as a whole. And then you can start applying them in every little bit of your game, which is going to make your life a lot easier. So this is going to be it for now for state trees, but don't be surprised when you see more state tree related content popping up on this channel in the future. And a very big thank you to all my Patreons. You can see them on screen right now. If you want to help support the channel or get any of the project files in any of my tutorials, there's a link down below to the Patreon page to support me, or alternatively as a YouTube member. And of course, an extra massive thank you to my Cave Digger tier supporters, Sir J. Thomas, and my Cave Student tier supporters, Oiku and Earl Monsville Urno.